Hi there, my name is Oleg Shelajev. You're watching J4K 2020, and this is a session GraalVM as a platform for cloud deployments. I work as a developer advocate for the GraalVM team at Oracle Labs at Oracle. And if you have any questions and you cannot catch me here, so you can find me on the internet. I go by @Shelajev almost universally. You can ask me all questions about GraalVM, software engineering, life in general, and I will try to answer myself, or I will pass it along to the smarter people working on the GraalVM team, and we'll figure it out. Please don't make any forward-going business decisions based on the contents of this presentation. It's a technical presentation, and also note that GraalVM native image is available under the early adopter status, so be mindful of that. Let's go. GraalVM is a high-performance polyglot multilingual virtual machine capable of running programs in different languages. Currently, we support JVM languages, JavaScript, Python, WebAssembly, R, Ruby. There is a community effort to bring Smalltalk into the GraalVM ecosystem, and many other languages. Most recently, I saw someone experimented with PHP. The GraalVM idea is that the runtime should be fast, so we try to run all those languages really fast, at least comparable or better than all the alternative means of running those. So, and GraalVM is really fulfilling this promise. It's a high-performance virtual machine, and we're going to explore how you can benefit from GraalVM project if you're a Java developer. For a Java developer, GraalVM gives a number of things, most notably the high-performance optimized just-in-time compiler, so the JIT, and you can run your Java applications with the GraalVM JIT, and they can be potentially faster. Typically, they're faster because it's a really good JIT. GraalVM also features the ahead-of-time compilation mode, the native image technology that can take your Java applications and feed them to the native image utility, and then analyze them and compile them ahead of time into the platform binary. This will be a standalone, self-sufficient file that you can throw into a minimal Docker image and run it, or just double-click on it, and it will run. It will not depend on the JVM, and it will feature a different performance characteristics from running Java with the JIT. And also, GraalVM is a multilingual engine, so you can run different languages, other languages, in the same process as your Java application, right? So you can maybe spice it up with some JavaScript scripts or maybe some Python scripts for machine learning, and you can run it inside a single process using a comprehensive polyglot API. For the Java developers, GraalVM most notably offers an option how you would like to run your applications. You can run it with a JIT using normal Java utility from the GraalVM distribution. It will run normally. It will set up the Java hotspot virtual machine, the same JVM that is coming from the OpenJDK project, and it will just use the GraalVM compiler as a top-tier optimizing JIT. Or you can, if you think that you are better benefiting from the ahead of time compilation, if you know what it does and if your use case requires that, then you can use the native image utility on your Java application and then execute that standalone binary file that it produces. The ability and this freedom to choose one of those is what makes GraalVM great for Java applications. Right? There is no limit. GraalVM doesn't tell you that you need to compile your applications ahead of time. GraalVM gives you both options, and you pick what you think is better for your deployment. When you run with the uh, JIT, right? This is approximately how it looks. It starts the Java hotspot virtual machine. It plugs in the GraalVM JIT compiler using the Jvmci, which is a JVM compiler interface, which was added to OpenJDK in the JAP 243 in Java 9. back in Java 9, right? And through those two layers, through those bottom two layers, we can run all the JVM applications. So you can run your Java applications, or you can run your applications in different languages. So Clojure, Kotlin, Groovy, Scala, Ceylon, or whatever other JVM languages you have. If it compiles to Java bytecode, you can run it on GraalVM. To support other languages, we needed to introduce more abstractions and more infrastructure. So there is a truffle framework, which is a framework for implementing managed languages. It allows you to write an interpreter for the language using Java. So you use Java to write an interpreter for example, Ruby, and then at runtime, those become compiled, just-in-time compiled into the machine code. So this way we have the interpreters, which is for Ruby or JavaScript, WebAssembly, and other languages that we support. And you need to understand here is that those interpreters are quite complex Java programs. They operate on very dynamic languages, Ruby or JavaScript or R, extremely dynamic. So they're the complex programs, and GraalVM JIT is able to optimize those programs at runtime very efficiently. So it can see through the abstractions and the complexity of those and create very efficient machine code. It also means that one of the corollaries from that is that on the normal Java bytecode, right, that normal Java programs produce, which is typically simpler than this combination of the interpreter and a very dynamic language program, GraalVM compiler shows itself really, really well as well. And a part of the reason for that is because it has to be really good to see through and understand the complexity of those dynamic interpreters for dynamic languages. How do you get all this goodness? Fairly simple, fairly simple. Let me just move my face away from there. You download GraalVM, you go to the graalvm.org/downloads, and you pick the version of what you want. You pick the operating system, and you pick the JDK base version. We currently support Java 8 and Java 11 based distributions. So if you're running one of those, you can just download GraalVM, unpack it, and then use it as a compatible out-of-the-box available JDK for your Java applications. So you unpack the archive, uh, and then you put it GraalVM on the path. You don't have to actually create the GraalVM directory, but it's convenient if you want to point your Java home environment variable to the same place. So you just export path the bin directory of the GraalVM distribution, and then you run your applications normally using Java -jar. And this Java executable will come from the GraalVM distribution because it's in the path. While we are thinking about this, can you please type in chat or give me another way to give me tell me in some other way which version do you run in production more? Is it Java 8? Is it Java 11? Or is it something else? I'll be absolutely ecstatic to know. But getting started is very, very simple here, right? It's the same way you start with any other JVM. The benefits you get is that you can get better performance out of it, right? Your Java applications can run faster. The GraalVM compiler is really, really good. So when you run your application for a period of time, the JVM will collect the profile, and eventually your code will reach the top tier optimizing JIT compiler, and it will compile that to machine code. So performance is money, and especially so in the cloud age, where when we deploy to the cloud, we do pay for the compute resources that we are using. We do pay for the compute resources that we're using, and the better your performance is, the less you can potentially pay to the cloud provider. This way, for example, Twitter is using the GraalVM compiler in production to run their Scala microservices, and they are showing great results. And you can find the VM engineers from Twitter VM engineering team going around conferences and having talks and writing articles how they use GraalVM compiler and what results they're getting. This is very interesting. Uh, Oracle Cloud Infrastructure at some point have migrated some of their programs to GraalVM. They showed better peak performance. They showed, very importantly, the less time spent in the garbage collection. This is probably because of the better escape analysis that GraalVM compiler has. And it also showed the seamless migration. So the GraalVM indeed has a compatible JDK, so you can just use it for your applications. You can read more about that in the blog. There you can see the URL there. But how we know that GraalVM is really good is we run a ton of benchmarks. Like we run really we we want GraalVM to be the best runtime for your Java applications. So we know that it needs to be fast. So we run a ton of benchmarks all the time. One benchmark seed that I can recommend is the Renaissance. Renaissance consists of the benchmarks from other projects, from other frameworks and libraries which are popular and which you might find in the modern Java applications. So you can see there is some Akka, there is some Scala, there is some Dotty compiler, there is some Neo4j, which is the graph database and a memory heavy workload. There are some reactor extensions, there are some RX Scrabble, the reactive extensions, and so on. Those are fairly new and popular applications and frameworks, and other benchmark suites might not feature the same code paths and the same code patterns that you can find running these benchmarks. Of course, it's very important to run the other existing uh, benchmarks that are established in the industry, the capo, spec JVM, and so on. But don't don't neglect the fact that if your benchmarks were written like 20 years ago, then probably it stresses the code how it was written, how we were writing Java like 20 years ago. So Renaissance uses the more modern application frameworks that you might find in your applications. In any case, more benchmarks is better. You just need to be very careful about the extrapolating the data you find in the benchmarks. So be mindful of that. But we know that GraalVM shows really good results on many workloads, and you can see some data here. It's also an open source benchmark suite, so you can just run it yourself if you wish. Let's talk about the cloud though. Some applications in the cloud are very different. So normally the JIT offers you the ability to run your applications for a long period of time. Now in the cloud, we do things differently. We pack everything into the containers. We put the containers very neatly into memory, and we constrain every container, every application, the resources available for every application. We constrain that very hard. We make it as small as possible, just to make it run. And the smaller we can go for every particular application, the better its performance is. Because in the cloud, we very often pay for the compute resources and for the memory, which means the smaller amount of resources we can use, the less we pay. So if you wish to look at uh, the graph here, or at the illustration of the graph here, there are different axes of what is good performance, what means fast. Some people think this is peak throughput, or some people care about the tail latencies and want them to be as small as possible. So in the cloud, we probably have this separation. Some services we want to run for a long time. We want to give them beefy machines. We care deeply about the tail latencies. We care deeply about the throughput, how many users we can service with a single instance of the runtime. And for other services, they are on the other side of this line. And there we want the lowest memory footprint we can get. We want to have an excellent startup speed and small packaging. Why? Because we want to package the services into small containers and then ship them into the managed environment where Kubernetes or Knative or some other service will orchestrate their deployment. and then scale them automatically back and forth depending on the traffic that you need to serve. This is very interesting because of this ephemeral nature of your application, you don't know whether it will run long enough to JIT compile everything that it needs. You don't know if it will run long enough or if it will run in the environment large enough to have resources to reach the peak throughput and the latency requirements that you can get. But you do know that your applications will be destroyed and created again and again and again. And maybe multiple instances of your application will be created again and again. So you value the three items on the left much more. The good thing is that GraalVM covers the whole thing here. So it gives you a choice. Remember, you can run with the JIT or you can run in the ahead of time compiled mode. Both of them are parts of the GraalVM offer for you. So you can choose what you want. Either you want startup speed, memory footprint, and small packaging, or you want peak throughput and uh, tail latencies. Of course, we're trying to get better all the time. So we would like to get the peak throughput on the ahead of time compiled applications better. But in general, it will be a little bit less than warmed up JIT performance. So let's talk about how you can get the benefits of the ahead of time compiler mode, because for the JIT is what's very simple. Unzip and go right into production. So ahead of time compilation, you need to use the native image utility, and there are two parts of the life cycle, right? You create the native image and you run the native image. And this is a very important difference of, of the GraalVM native image compared to your normal Java execution. What it gives you the excellent runtime characteristics for the cloud specifically. You can see here, the sample micronut application starts up in like less than 100 milliseconds with the small environment. I was giving it just 64 megabytes for the heap, and it still started really strong here with just 70 milliseconds. This is a microservice that is ready to serve my HTTP traffic here, and I think it's a very good result. You can literally put it into the smallest the smallest function as a service runtime that many cloud providers offer, which is typically 128 megabytes of memory, and it will do really well there as well. How does it do it? It takes your application classes, it takes your libraries, it takes your JDK classes, and it takes the runtime components from the Substrate VM project, and it takes like all those things are written in Java. So native image looks at all that Java code and it starts initializing your application. It figures out which classes will need to be present in the output, which classes are actually being used, which fields and methods are actually being referred in the final, in the actual at runtime of your application. Then it initializes the application and it takes a snapshot of that. So it compiles the code that is reachable ahead of time using the GraalVM compiler and writes it out. And it also takes the heap snapshot, so-called the image heap, and all the initialized objects which have to be present will be written in memory. So when your application, when you start your native executable, the results of the native image, those will be already available there. You don't need to spend time reinitializing those. That could be a simple date time format, or it could be your currencies or your time zone, or it could be your complex data structures that you can pre-initialize in the native image. Of course, the more objects you initialize, the larger will be the output of the native image, but that is a separate question. So in the end, there is a compiled code and there's some data sitting in memory. How is it possible to do this on the bytecode level? So GraalVM runs the point to analysis on all the bytecodes, and it works under the closed world assumption. That means that when your native image process runs, it assumes that it has seen all the bytecode that will ever be executed in your application. It allows us to do aggressive ahead of time optimizations. For example, we if you see all the bytecodes, you know exactly the class hierarchy. You know that the class hierarchy will never change because there will be no additional bytecode. It will also allow us to remove the unused classes and objects very aggressively. And also, it will allow us to save memory and save CPU cycles by removing the infrastructure necessary to deal with the bytecode at runtime. If everything is precompiled and there is no new bytecode ever in our application, then we don't need the JIT compiler. We don't need the class loader and so on. The sort of a downside of that is that the dynamic parts of the language require configuration. So if you want to access something through unspecified reflection, or if you want to use proxy interfaces, or if you call the resources, you need to provide a configuration. This is not hard, and there is a tool called there is a Java agent-based tool that you can use to generate that configuration for you. So you can just run your Java applications using the Java process and specify the Java agent parameter, and then you will execute the code and it will record all those dynamic parts that needs configuring, and it will output the configuration for you. You can then edit that configuration if you wish, but the bulk of the configuration will be there for you. And of course, the most obvious restriction of the closed world assumption is that there will be no new classes loading at runtime, which could be seen as a good thing because the immutability of this could could mean better security of the service. If there's no new classes loaded, there could be no new threats, so to speak. Right. So these two graphs show you the differences of the performance between in the beginning of the runtime between the micronut example microservice running in the ahead of time mode and the JIT mode. You can see that in the ahead of time compiled mode, it consumes just a few dozens of megabytes of memory. This is the full memory of the process, currently somewhere between 30 and 35. This is not just the heap, it's the full memory that the operating system sees the process consume. And also the CPU of this, the CPU is only doing a little bit of work when the request comes. So this task here is to wait for the application to run, and then sleep a second, do a request, sleep a second, do another request, sleep a second, do another request, sleep a second. So you can see that with the ahead of time compiled mode, the application just finishes this whole test in 4 seconds. So there are like 4 sleeps and then force the request. In digit mode, the situation is a little bit different. So at the startup, you can see a lot of CPU usage. This is the JVM starting up. It has to do unnecessary things for the startup, and then the memory spikes a little bit larger. It sits at a very modest 150 megabytes of the total memory size for this particular test, which is, I think, a really, really good result. But it also like what 5 times larger than the ahead of time compiled example. You also can see that there is a lot of CPU, and when the first request starts coming, this is the second red spike on the right there, and you can see that it's also features a lot of work that CPU has done. So this is uh, the application starts serving your request, the new code paths have been executed, so the JIT compiler starts doing some work, and so on. So this is the difference. This is the difference between those two. The native image support in the ecosystem is quite extensive. There are a number of frameworks which support GraalVM native image and work with GraalVM native images. There is Helidon, which is a micro-profile based framework and a collection of libraries for creating microservices. There is Micronut, which takes a very interesting approach and have a demo of the Micronut applications. We'll talk a little bit about this in a second. Of course, there's a Quarkus framework. There is a Pico CLI framework for creating creating Java command line applications. So and it works with GraalVM native images really well. So if you want a command line application, you can use Pico CLI and GraalVM. And also the support for native images in Spring applications is in the works. And I know this is a very interesting topic for many of us. So I would wholeheartedly recommend the session from the recent Spring One conference, the path towards Spring Boot native applications by Sebastian Deluze and Andy Clement. And they showed the current state of the art was about using GraalVM native images and Spring applications, how to get started, what are the challenges, what is the work that is being done to bring native images and Spring applications together. But they also outlined that native images bring really good benefits for running your programs in the cloud. Instant startup, reduced memory consumption. You can watch that session on YouTube. It's available there. But in general, the benefits of the startup time and memory come not from the choosing the particular framework. Of course, there are differences, but those differences are the performance differences are rather negligible compared to moving from running in the JIT mode to running as a GraalVM native image. The memory footprint story is approximately similar. These were very simple hello world tests, and you can see that it goes very much into the smaller size compared to running on the normal JDK. Let's talk about Micronet. Let's get to the demo because I want to show you how you can run your applications both in JIT mode and in the native image mode based on the example of a Micronet application. So micronet is microservices in the serverless focused framework. And it's a complete application framework that offers you the dependency injection, the aspect-oriented programming, configuration management, beam introspection, and everything that an application framework you would expect an application framework to offer. Metrics, different backends for the metrics, and so on. The very interesting thing that makes Micronet stand out is that it pre-computes a lot of data that is usually only available at runtime. So it uses annotation processors and it pre-computes the dependency injection path and code. It pre-computes the annotation metadata, proxies, it pre-computes beam introspection things, and essentially, this is what you would expect the framework, the web application framework in Java do at runtime, in the beginning of runtime, create the context and so on. Micronet does that using the pre-computation on the annotation processor. And this is very good. So I would like to go to the demo now and show you a Micronet application. So we'll go through the following things because I want to show you how you can get the best from your Java runtime and the best from your native images. So this is what we'll do. We will go and see a sample Micronet application. We will build a native image out of that application. We will run this application using Java with the JIT. We'll record the baseline of the performance. Then we will use the G1 GC based GC in the native images. And I will show you how to tweak memory settings for your native image so it will use more appropriate amount of memory. And we'll use the profile guided optimizations, which is a technique where we can record the profile ahead of time and then apply that workload profile when build your native image memory. And we'll see a little bit more realistic example of the same application. Let's get to it. Yay, we got to the demo. First of all, let's create a sample Micronet application to experiment with the GraalVM native image. We'll go to micronet.io.launch, which is the website where you can generate your Micronet project. We'll keep everything here. The important part is that you want to add the features and you add GraalVM, which allows you to build GraalVM native image application here. So just select that, done, and you can see the diff between the projects, the default starter and what you have selected. So it adds GraalVM to the feature list, changes some Docker containers, but most importantly, it adds the annotation processor and the dependencies to include the bits necessary to configure GraalVM native image. Then you just download, you generate the project, and you're ready to open it in your IDE. I have my Visual Studio Code here. I have my project. It is configured and set up on a cloud machine, which is a fairly powerful instance that they can have here. So it has plenty of RAM and it has 16 threads. So decent. This is where we're gonna experiment with our code. Micronut here is used as the framework for building a small microservice. So I have added a controller that computes the prime numbers. This is fairly simple. There is a number of a method to check if a number is prime, which is checking whether it's divisible by stuff. There is a member for prime sequence, which just creates a sequence and filters the prime numbers and collects them to a list. And then two main methods, which are either select the primes, count the primes, and then randomly set the upper bound and return the primes. Let's see how it works. I'll open my terminal here. I'll have my bash task. Let's see. I have a bunch of files here. This is a Gradle project, so I can build it with Gradle w build. But what I want to show is I'm running my Java is a GraalVM distribution of Java, so it's based on JDK 11 and it's GraalVM Enterprise Edition 20.2. And it also I have my native image command there, native image version. It's also in the same distribution. So now what I can do java -jar build libs and then primes are cool all jar file. This will start my micronut application. You can see that it's a powerful machine. Micronut is really good for startup. So it starts, it's just under a second, and I can now access this on my server. I'm gonna click here, and it doesn't have the root thing, but I can see and I can tell you that if I had hit the primes random and then a number, it gives me like a sort of a range between two random numbers, and all those numbers are primes. Now, this is all good and nice. What we can do, we can build a native image out of this application. So here's the script how I would do that on this particular micronut application. I will build it with Gradle, and then I will run native image and give the name for our executable, and then I would pass the class path to it, and then I will just say that's the number. I'm gonna run this script right here, build native image. I just want to show to you once. I will not build all the images we need here, because that will take 40 seconds and time is precious. So we are building the Gradle thing, and we will get the result, and we start building the native image. You can see that during the building the native image, it does actually quite a bit of work. So it sets up the thing, it lists the class paths, figures the universe of the object that it needs to analyze, and it will take a little bit of time. I think in my experience, this should take something like 40 seconds, but we'll see. You can also see that this script, the native image command, prints out the memory usage that it consumes during the build. So currently it's at 1 gigabyte, and it can quickly become a much larger number. So I would recommend you build native images using a larger cloud instance or a powerful machine, because it can, if you give it more resources, it can consume more resources. You can also limit this number, right? But if you give it more resources, it can have more resources, and the build will progress faster. So all in all, it should be finalizing itself now. So you can see here that it created the objects, it figures out the type flow, then it ran the analysis, and then now it's doing the inlining and the compilation, the actual ahead of time compilation of the code happening right now. And in a moment we will have our primes serial output. It's called serial because by default it includes a sort of a serial generational scavenger garbage collection algorithm, which is simpler to implement, and it also features really good results because it doesn't interfere with execution of your program when it's not actually running the GC. The downside of this approach is that when it does run the GC, then it somewhat like it can be susceptible to the GC pauses. So we have it here now. We can see that there is a prime serial. I will run it. I'm running it right now. You can see that it starts in a whooping 24 seconds, 24 milliseconds. Sorry, and I can access the same URL there. So I will go to my browser and I can show you that I can see the same numbers. The numbers are the same because the seed for the prime generator is built in here, specifically created this way. So when I do load tests, it does show consistent results. So what I can do now, I can now use a test script here, which will run my executable, and then wait for it to figure out things, and then run the hey load testing tool, and then report the results back to me. Let's try this. I'm gonna copy this script here, and I will limit my memory consumption of the heap of my application there to 200 megabytes, 256 megabytes. Now the load test will take 30 seconds. We could actually lower this number because the application doesn't need to warm up, right? It just needs to create some load to figure out whether the GC could be the problem or not, but it goes fairly quick. So you can see that in a moment, this will be printing out the results at us. So what it does, it just hits my application with as many requests as it can serve and notices the latency distribution for my application. So you can see that most of the requests, almost all the requests, were very fast. Some of them were a little bit slower, but this is just still, this is what, 50 milliseconds. And we can see that we served around 5,000 requests per second. Now, I've built the similar applications here using the G1 garbage collector. So I have the low latency garbage collector specified, and I also built my native image using the low latency garbage collector and also profile guided optimizations. So what I did, I specified that, and I said that I would like to have an instrumented image. Then I run the instrumented image under load, and it will generate me a profile file. So I store those profile files for a couple of different URLs, and then when I generate the second native image, I specify those and show that I would like to keep those profile in mind while building this image. The profile guide optimizations are an enterprise feature of GraalVM. Enterprise low latency garbage collection is as well, but we're showcasing technology here, so bear with me. What I need to do, I will do the same test, but I will just run it with the profile guide optimization thing built in, and in 30 seconds we will see the impact and we will see whether it makes sense to do those. So again, the application starts really, really fast. It takes just a couple of milliseconds. The startup times are comparable to native and applications written in languages like Go, which is very good. And also performance of the applications are really good. Both, like, so the PGO and garbage collector improves things, but even the just default configuration has very decent performance. So we here, like, we're at the end of the script, almost carrying the results. What we see here is that, again, the distribution is spectacular. The response times, there is no slowdown in the beginning because everything is precompiled. And also we can see that the number of requests per second is almost tripled from applying the profile guided optimizations, and the J1GC based garbage collection. This particular workload, just I want to say, is a little bit susceptible to the GC configuration. So in this case, our application generated a lot of load in the young generation, and almost none of that survived into the old generation. So J1GC has the benefit of being adaptive, so it can configure young generation to be as large as needed at runtime. With the serial garbage collector, with a generational scavenger, there is a predefined young generation size. So in this use case, it runs a little bit out of space there too often, so it all the time does J1GC, does the young generation cleanups, which takes performance away from it. So for the best results, use the profile guided optimizations, use the J1GC garbage collection because it's adaptive. You don't need to configure your application for the particular workload. And in any case, use native image because you get really good results. And also you get a very good memory usage. Thank you very much. This was a demo. We're back. Oh, that was a demo of the sample micronet application. It was really good. I thought it was interesting. So we saw that there are a number of things that you can do to make performance of GraalVM native images better. And I think this is very important because if you want to rely on the project to be a platform for your application, you better make use of it properly. You better use it with an expert knowledge of things. So here is a short takeaway cheat sheet, so to speak, what you can do with it. So first, for the native image, you want to configure your application runtime memory usage. You want to use the same options that you use for your hotspot VM, right? You want to limit the max memory, you want to limit the new generation size. If possible, use J1GC based GC, not because it's much better at improving the throughput of your application, but because it's adaptive, so you can put it in a constrained environment and it will figure the settings that it needs to apply by itself. Use the profile guided optimizations because you will get better throughput and you'll get better tail latencies because you can serve requests faster. And also what you want to do is not just look at the throughput factors or at the latency, but you want to minimize the ratio between how much resources you give to the application and what is the throughput that you get back. This is the metric that you want to minimize. So it's a resources to serve users, uh, which might not be as obvious as it sounds in retrospect. And while we're talking here, I would like to give you a few takeaways about running with the JIT as well. So if you want your application to be really good for the JIT, and this is not just for GraalVM JIT, because those are general performance advice here. Right? You want to write small methods, which is very important. The compiler is really good at inlining the methods, so you can take small methods and put them into the larger method, but it's kind of awkward for the compiler to do otherwise. Splitting larger methods into small chunks is not something the compiler does naturally. Remember that the local allocations of data is almost free, so if you do new something object, you don't need to worry about that. On the hot path, most probably that allocation will be eliminated anyway. And of course, do not hand optimize your application. You try to reach the runtime team and ask them whether they can improve the performance of the certain workloads in general for all the users of the same framework or the same library technology. And as the final advice, if you're using GraalVM as your platform, then for best throughput, for best of the best warmed up performance, you want to use and run your Java applications with the GraalVM JIT. And if you value startup and memory footprint for your small ephemeral applications, GraalVM native images is the technology that you want to use for your deployment. So this was what GraalVM can do for you as Java developers, and this is how GraalVM can power your Java microservices and your Java workloads in general, not just microservices. You cannot forget that the JIT there is really, really good. And if you just run your applications normally, there is no there is no reason not to look at GraalVM and not to try it. And we can talk about the other languages and everything else, but at the heart of the GraalVM project, there is certainly the compiler that can make your applications run faster. There's an Oracle GraalVM Enterprise Edition, which is a product by Oracle, which you can use. It gives you even better performance. The compiler there is even smarter. It gives you enhanced security for native code. It gives you support from the GraalVM team, and it's really good. You can look into that. You can also go and connect with the GraalVM. You can find us on graalvm.org. You can follow us on Twitter. We go by @GraalVM. You can download and use GraalVM or evaluate GraalVM for your applications. And this is something that you should do absolutely uh, because it's really good. Thank you very much. This was Oleg Shelajev, and you were watching J4K 2020. Thanks.